All right, good afternoon. So this is the last lecture on sequential machines, and today we are going to look at concurrency issues. How to deal with when we have concurrent activities, which we haven't seen so far very much. So let's start out with a very simple observation. When you're designing something, say a large combinational circuit, you often have several options, and in fact many of those options involve turning the combinational circuit into a sequential one. So suppose you have this circuit which is composed of these three boxes, F1, F2, F3, pure combinational boxes, and you are streaming it, so there is inputs coming in constantly and you are taking them out. A pipeline, so this looks like this, an input comes in, it goes inside, and the next input that comes in cannot enter the circuit until the first one leaves the circuit, right? So this will go in only after the red one has left. If you contrast this with a pipeline version of the circuit, where all I have done is inserted two FIFOs in between stages of this combinational circuit, what you will find is the first one comes in, it goes here, and then the next one comes in, and simultaneously now you have two tokens in this system, red one and green one. They're being processed concurrently, right? And then more tokens can come in, so there are three stages here, so you can have as many as 3 packets being processed simultaneously in the system, and then they will leave the system one by one. So this is a very standard thing, and we will be studying more about it later in the course. And you have also seen examples of folded circuits. Multiply by repeated addition was a good example of that, where a token comes in and it goes around a few times, right? And then it leaves, and only then the next one can enter. Okay, so why are we looking at these design alternatives? Why are people just not happy with the first one or the last one? Why do we go from one to the other? And there are very, very good reasons for it. And to understand, you have to understand some other properties of the systems, which are very high level properties of the system, because that depends on what you're computing, some property of what you're computing. So for example, latency is defined as some input enters the system and how long does it take before it comes out. So we say the latency of processing a single input is such and such, all right? But sometimes we are equally interested in throughput. We want to know how many answers can be produced, every second from the circuit. How soon can I inject the next one into the system? And let's try to understand these three design alternatives from the point of view of from the point of view of these two properties, latency and throughput. Okay, so let's assume the latency of each of these combinational boxes is 5 nanoseconds. Let's assume that it takes about 1 second to, 1 nanosecond to NQ or DQ from a FIFO, and mux takes 1 nanosecond, and register takes 1 nanosecond. The point I'm about to make is not dependent on these specific values. This is just for illustrative purposes. All right, so now I can analyze these alternatives. So let's focus on the latency first of 3 designs. So first one I'm calling combinational. So how long will it take for an input to enter and leave? So we're assuming 1 nanosecond in the FIFO, and then 5 plus 5 plus 5, so 3 times 5, and then plus 1 more as it leaves in the last FIFO. Make sense? So that adds up to 17. Now what about the second one? What about the second one? So it's almost like the first one, except that you have these two FIFOs in between where also you are spending one cycle each. So therefore it is 1 times 1 plus 3 times 5 plus 1 as opposed to 3 times 5. And then you add one more at the end again. And if you do it like that, then it comes to, it sums to 19. And what about the last case, the folded one? So something will come in when it goes round, so that's 5 nanoseconds, and we are assuming the mux takes a cycle and storing it in the register takes another cycle. So by the time you add all that, it is 3 times 7 in that case, and the total latency is 23. So if you were just interested in latency, obviously you were better off using the first one, right? Because it has the shortest latency. But now let's look at the throughput. Throughput is 1 over latency. So what you see in this case is the latency of the throughput of the first one will be every 17 cycles it will produce a value. The pipeline one will produce a value every 6 cycles. Much higher throughput than the first one. So that's something desirable. If you are trying to process lots of things, we worry about the total time of processing n things. And if you can keep shoving it in, every 6 cycles, obviously whole thing is going to run much, the total time to process n quantities will be much lower. In the last one, its throughput is low, right? 1 over 23. So now you are wondering, why does anybody care about these folded circuits? All right, we'll come to that. But you can see now what will be the clock period of various circuits. What is the clock period of the first one? Does anybody remember how clock period is defined? What is the minimum clock period? It has to be the longest combinational path between 2 registers. So in this case you have FIFOs, and in the first case you have 3 combinational things in the additive form, so it becomes 15 or 16 or something, So you have the minimum clock cycle here will be 16 nanoseconds before the clock can change, because that's the propagation delay through these 3 combinational blobs. On the other hand, if you see the second one, right, in the pipeline one, what is the maximum logic between 2 units? It's 5 plus 1, so it's 6. Much faster than the first one. And the second one is also quite fast, right, because you have to only go through one of these combinational circuits plus mux to go round and round in that case. Picture is getting more complicated, right? So you can process less, but you can run the clock faster. In case of pipeline circuit, what you saw was that the throughput went up quite high. So depending on what our goal is. And then we can ask, why do we want to worry about folded circuit? It should be obvious that if I'm looking at the area of the folded circuit should be the lowest, right? Because instead of using 3 separate combinational things, F1, F2, F3, I'm just reusing the same circuit over and over again in this case. So that's what you saw in multiply by repeated addition, right? That we could get away with having just one adder, 32-bit adder circuit, because we just kept the results in a register and used it over and over again. So it's smaller than if you had a combinational multiply circuit. So these are the design alternatives which we will explore as we go along in this class. This was just a very high level view to tell you that there is something like this, and when you are looking at especially the second one, there are serious concurrency issues, right? Because you're processing multiple tokens simultaneously in the system. So we have to worry about that. Okay, so in this pipeline system, which is the first one I showed, second one I showed you, if I had to write a Bluespec program for it, it's pretty trivial. what does this code show? What is the rule first? A rule for stage 1. It picks things from the input queue, transforms it by F1 and puts it in FIFO1. What is the second rule, stage 2 rule? It picks things up from FIFO1, transforms it by F2 and puts it in FIFO2. And similarly for the last stage. Yes? It's a very flexible pipeline, because if some rule doesn't execute, that's okay. You will not pick up anything from the input queue, and you will not put anything in the output queue. Now there are many questions we can ask about this circuit. The first, most natural question is, when can rule 1 fire? When can rule 1 fire? Anyone? Yes?
Rule 1 can fire when there's something in queue and when there's room in the FIFO 1.
Fantastic, right? There has to be something in the input queue and some space in the output queue, and this is what we call implicit guards, right? I mean, system already checks all these things to do that. All right, very good. Next question I can ask is, can these 3 rules execute concurrently? Can you be computing in the first stage and the second stage and the third stage at the same time? Any opinions? Speak up. Yep.
You could, as long as you make sure that it's done in a reasonable atomic order, kind of.
Right. I mean, conceptually it seems we should be able to execute these rules together, right? While the first stage is moving something here, second stage is moving something here, third stage is moving something here. So the answer is yes, provided this boundary, this FIFO, has some properties, like the NQ and DQ in it must be allowed to happen concurrently. Because if NQ and DQ can't happen concurrently, then either this rule will fire or that rule will fire. Both cannot fire at the same time, because one is trying to NQ, the other one is trying to DQ from the FIFO. So as long as FIFO has the right property, you should be able to execute these rules concurrently. Well, let's assume that FIFO doesn't have the right properties. Can rules 1 and 3 fire together, assuming you have enough tokens and spaces and so on? Notice stage 1 rule and stage 3 rule do not interact with each other. This guy is putting something in FIFO 1 and this guy is taking something away from FIFO 2. So there is no interaction. So as long as you have tokens sitting in these queues and empty spaces in the output queue, yes, these rules can fire concurrently, even if FIFO doesn't allow, the same FIFO doesn't allow concurrent NQ and DQ. Okay, so this example is my motivating example today to try to understand what are the rules of the game when we have multi-rule systems, when we want to execute multiple rules simultaneously, concurrently. Okay? All right. So before I move on, I'd just like to point out, if you wrote this code and it turned out that really these rules cannot execute concurrently, it's really not a pipeline system. I mean, it's kind of a bogus thing. Yes, you wrote a very wonderful description, but we didn't achieve our goal, because the reason we were designing this thing is because we wanted everything to move concurrently in this queue. We wanted to process multiple things, and if only one rule is executing at a time, or only one rule can execute at a time, it's not a very good system. It's not a pipeline system. So it may look like a performance thing, but this performance issue is so tightly coupled with functionality also, right, that we have to, if we can't do it in a pipeline manner, we should not call it a pipeline system. So for pipeline systems, it's essential that these rules be able to fire concurrently. Good. Multi-rule systems. So most systems you have seen so far either had one rule, or if it had multiple rules, they were mutually exclusive. Only one of them could execute at any given time. So really, there was no issue here, because all the systems you have designed so far, or you have seen so far, had one rule, and then we understand, take the rule, execute it, it transforms the state, and then we go and look at the system again to see which of those 2 rules or 3 rules can fire at any given time. All right. Now we are going to look at a system with multiple rules, just like the one I showed you, right? And the question I want to answer in today's lecture is, when can 2 rules fire concurrently? What does it mean to execute 2 rules concurrently? And what does the hardware look like when multiple rules fire together? So that is the basic question we are after today, that if I write a multiple rule system, I want to understand if these rules can execute concurrently. And if these rules execute concurrently, what does the hardware look like? Very good. Now it may look like that I'm backpedaling a bit, but this is something which is very, very important. So in Bluespec, if I write a multi-rule system, it behaves as if one rule executed at a time. So you may have many rules which are enabled. We say just pick one and execute that one. And when you execute that rule, it will change the state of the system. And if it changes the state of the system, then we go and it may enable more rules. So we go and ask the question, which rule should we execute next? So we just do this thing repeatedly. We execute a rule, see what state changes are to be made. We make those state changes, ask the question again. So this is the loop every Bluespec design is constantly going. We call these semantics one rule at a time semantics. Why? Because if a behavior cannot be seen in this manner, if a behavior you observe on your machine cannot be explained in terms of one rule at a time, it's an illegal behavior. There is some problem in the implementation. And the way Bluespec is set up right now is it will be a compiler error. So when compiler tries to execute many rules together, it will make sure that the final answer conforms to some sequential execution of the rules. Is this high-level point clear to everyone? One rule at a time semantics. One rule at a time defines, what is the meaning of a program. Not in any specific order, any order. So there may be many possibilities there. But then, for performance reasons, we may want to execute many rules together. So I'm setting up an abstract problem for you. And the problem simply is that I have multiple rules, many of them are ready to go. Bluespec semantics says do it one at a time. And if I do it one at a time, I get some answer. I do them concurrently, whatever that means. I'll explain that in a second, right? The answer I get doesn't match with any of those answers. Then the concurrent execution was illegal, not allowed. Bluespec compiler just won't do it for you. So we're going to get to the bottom of this question today. So concurrent execution of the rule, and here is my running examples for this lecture. So we have 2 rules can execute concurrently if the concurrent execution would not cause a double write error. Seems sensible thing to do. And the final state can be obtained by executing rules one at a time in some sequential order. Okay, so what are these examples? They differ just slightly. They're contrived examples just to illustrate the point about concurrent execution. So in the first rule, RA, example 1, RA is being incremented by 1, and in RB, Y is being incremented by 2. In example 2, x and y interact. So x takes the value of y and increments it by 1 and stores it. In the second rule, it takes the value of x, increments it by 1 and stores it. And in the last one, something else is going on, right? So these are very, very closely related examples, and the question I'm asking is, which rules can be executed in these examples? Can RA and RB be executed concurrently? Okay, without violating one rule at a time semantics. So how do I study this question? So suppose first I want to understand concurrent execution. I want to execute RA and RB together. Well, it's very simple. Then what I do is I have labeled everything on the right hand side of assignments with T, right, current value. And on the left hand side I have labeled it T plus 1, right? So you have xt plus 1 gets xt plus 1. Does that make sense? Right? I mean, everything you have been seen about rules is you look at the current state, do the computation, and you update the state at the rising edge, right? Which you'll see next time, xt plus 1. So if you do all this, and then ask the question, what is the answer that will be produced, assuming initial value of x and y is 0, 0. So what will happen in the first one? You will put in 0 for xt, and xt1 will be 1. You will put in 0 for yt, and yt plus 1 will be 2, right? So you will get this. What about the second one, example 2? You do the substitution for xt, right, and yt on the right hand side, you evaluate the things, and it turns out in this case that also will produce the same answer, concurrent execution of these two rules. And here also it produces the same answer. So in these three examples, these contrived examples, if you do concurrent execution of these things, you always get 1, 2 as the answer. 1 will be the value of x after you have done the executions of both rules, and y will be the value of y will have value 2. Now suppose I want to see if these concurrently executed values match, if these rules were done one at a time. So I'm going to consider two cases. I do rule RA and then I do rule RB. And the second case I will consider is I do rule RB and then I do rule RA. All right, so let's look at the next slide. I'm doing RA before RB. Please pay attention to these red things. I don't know if you can read it from where you are sitting. So I'm doing RA first. So in the first cycle, you will take xt value and produce xt plus 1. I'm looking at example 1. And then in the second cycle, you will take the value of, I wrote down yt1 over there, but there is no yt1, you didn't assign to it. So when I don't assign anything to something, then its value is exactly what it was in the previous cycle. So yt1 in this example is same as yt, because it didn't change, you didn't do any assignment to it. So I took yt1, added 2 to it, and then a yt plus 2 will get 2. Okay, so the final answer is 1, 2 again. Okay. Now tell me what happens in the second case. In the second case, you're going to compute the value of xt plus 1 will be 1, right? Now tell me what will be the value of y plus yt2, right? It will be 3. Does everybody see that? Right, because I changed the value of x, which I'm using again in the next cycle, so I'll get the value 1, 3 over here. And what happens in the last case? Okay, in the last case, I will get x to be 1 and y to be 2. So what does this, just looking at these numbers, what does it tell you? Well, so far so good. The concurrent execution in the first case produced the same answer as if you executed RA before RB. In the second case, it didn't match. All right? Well, maybe we were unlucky. We should try RB less than RA. Right? Because it says any sequential order is fine. All right? And in the last case, it matches again. So if we executed it concurrently, right, we get the same answer as the one we got by executing RA before RB. Let's try the third case here. When I execute RB before I execute RA, and you can work out all the subscripts here, because all I did was I numbered the subscripts in the rule RB first, and then I use the subscript above to number them 2s, and so on. And if you do that, what you will find is you again get 1, 2 in this case, and you get 3, 2 in this case, and you get 3, 2 in this case. Very interesting. So this is a very concrete experiment we just did, right? If we execute them concurrently, we get some value. And if we execute RA before RB, we get some value. And if we execute RB before RA, we get some values. So what can we say about the concurrency properties of these two rules? So notice in this case, in the first case, concurrent execution matches RA before RB. It also matches RB before RA. That is great. It's saying, look man, it doesn't matter what order you execute them in. It's the same as concurrent execution, and therefore we call this thing, these rules are conflict free. They can execute, and then you go and look at the code, you say, of course dummy, you know, X has nothing to do with Y, Y has nothing to do with X. Big deal. But you know, this is the professorial thing, you know, we like to explain things not intuitively but go over all the details, but you have to understand the mechanics of how I derive this. All right, what about the second one? Does concurrent execution match RA before RB? No. Does it match RB before RA? No. So we say these two rules are conflicting. Good? Everybody understands this. The third case is even more interesting. The concurrent execution matches RA before RB, but it doesn't match RB before RA. So therefore we will say that when you execute these rules concurrently, it behaves as if RA happened before RB. Got it? It's okay to execute them concurrently. Just remember, if you execute them concurrently, the behavior you're going to get is as if RA happened and then RB happened. So I have summarized it by writing RA less than RB in this, and this information is summarized in the conflict matrix, right? So here it says, well, you know, diagonal is understandable. RA conflicts with RA, RB conflicts with RB, right? But the interesting thing is RA doesn't conflict with RB. And the lower part is symmetrical, it's the dual of it, right? So RA was less than conflict free, it's conflict free other way too. In this case, C means rules cannot be executed concurrently, CF means rules can be executed concurrently. The net effect is the same regardless of what order you execute them in. And now when I look at the second one, they're all C's. They're saying you cannot execute rule RA and RB concurrently in this case. And in the final case, it's this, which means that if you executed RA and RB together, it will behave as if RA happened before RB. So conflict matrix essentially is pairwise description of these properties. It's telling you any two rules, how do they interact, whether they conflict or not conflict, or is one less than the other. Okay. Now I come to the second question. So I've given you a glimpse of how this thing is deduced. In fact, compiler does it for you, right? So I'm teaching you this stuff because I want you to understand, but you don't have to do it by hand, though on quizzes it's a different matter. All right, so now let's look at how will I use this information to generate hardware from it. So let's look at these two rules. Okay, some very elementary stuff. We have two registers, X and Y, and when I compile the first rule, I'm feeding it, oh, this is example 2, sorry, okay. So I'm feeding it X, and I'm just connecting it directly, and every rule has a guard, right? So in this case, the guard is true. I'm just calling it the rule of guard. RA is true. RA.ready is true. All right, and what is Y? Y is simply, similar thing. You increment it by 2, its guard is also true, and now you can connect X and Y together, so that Y means the output of this, and that X means output of this. So this is our sequential circuit almost. It's not complete yet. Because remember, I have said we always have to specify the enable signal for a register, because unless the enable is true, it's not going to change its value. So enable is essential part of the specification. So when is rule RA enabled? Always, right? I mean, it can execute any time you want. So, we have to figure out how we should connect it. Same thing is true for rule RB, because these rules had no guards in them. They were always true, etc. So here is the idea to complete this picture. I say, look, as long as the ready signal is true for this rule, you can enable it. That's like saying that connect RA ready to RA enable, and similarly RB enable to RB enable, RB ready to RB enable, which I can show by just drawing the circuits here, right? I draw those, if you didn't see it, those are those dotted lines connecting these things. Okay. Now this is wonderful. What this will do is, this is executing these rules concurrently. Now if you execute these rules concurrently, this would be correct execution, this will be correct hardware if rules RA and RB were conflict free, because they were allowed to execute in parallel. What do we know about this rule, this example? If you look at the conflict matrix of it, it tells you that rule RA and RB actually conflict with each other. So we have a problem. Our circuit is doing something, right? It's executing these rules concurrently, but the answers it produces have nothing to do with one rule at a time semantics. So this is that oops moment, things look very easy, we could generate the circuit, connect it, but it doesn't produce the right answer. Right answer being defined using one rule at a time semantics. So how do I solve this problem? how do I solve this problem? Let's think at a high level for a moment. You have bunch of rules, right? And these bunch of rules, they're all ready to go. If they were conflict free, we'll say go, right? Because whatever answer they produce is fine. But if they conflict, if two rules conflict, then what do we have to do? We have to choose either rule RA to execute or choose rule RB to execute. One rule at a time. We can execute RA and that will change the state, and after that we can ask the question again, which rule should we execute? Okay, so that's what we want to do. The question is, how do we do it? What is the hardware for it? So this is where another piece of hardware comes in, which is known as scheduler, right? It's a very simple logic, but you have to understand conceptually what it does. So what I'm going to do is I'm going to connect ready signals of all the rules to the scheduler. So take the green signals coming out of every rule, and so now scheduler knows these are the rules which are ready to go. In other words, amongst these rules, all the green values which are 1, that's the one that wants to execute right now. Can I let all of them go? Suppose both of them are true. No, I can let both of them go only if they're conflict free. So then what I do is, using the conflict matrix, the scheduler lets only non-conflicting rules proceed. In other words, the signals that come out of it, I haven't told you what's going on inside the scheduler, right? But it's going to maintain some invariant. Its job is to look at all the rules that are ready to go and then tell me which rules actually can go in parallel at that point. Okay, so that's what we are trying to understand, how scheduler is going to do that. Otherwise, it's very, very simple. Okay, so sometimes people refer to the signals going into the scheduler as can fire. These are the rules which are ready to go. And on the right hand side, enable signals are the ones, these rules will fire. They can actually execute in that cycle. Okay, scheduler is a pure combinational circuit with a small number of gates, and a correct but low performance scheduler may just execute one rule at a time, right? Nobody said that was illegal, it's just low performance, because high performance circuits, we want to execute as many things as possible concurrently. So let me show you some example schedulers. So these 3 examples are taken from what I have been discussing so far, and I had already given you the conflict matrix for this. So what does the first one say? What does example 1 conflict matrix says? It says RA and RB are conflict free. So as long as RA is enabled, it can go, right? As long as RB is enabled, it can go. So they're just connected like that, straight wires. So for the example 1, indeed it is direct connection between RA and RB. But example 2 is where we have conflicts. So when we have a conflict, in this case, okay, then RA can be connected to RA enable. But if we do that, then we cannot execute RB because it conflicts with it. So we'll have to take a note of that. Say, don't do it. Right? So what this is making sure is if RA goes, then RB will not go. On the other hand, if RA doesn't go and RB is ready, then RB can go. But if both are ready, only RA will go. So in some sense, I'm giving a priority to RA, but I could have easily designed a different scheduler like this, which gives priority to RB. RB will go and it will block RA from executing. So this is a choice, compiler makes for you. It'll probably give you a warning saying that there is a choice here. What do you want, right? If you don't say anything, then it picks the order in textual order, whatever order you wrote it in. Now the last case is also very interesting. Does anybody remember the meaning of less than? RA less than RB, what does it mean? Yes?
RA should go before RB if we do that sequentially.
So it says that you can execute them concurrently, and the functionality will be as if RA happened before RB. So what does the scheduler do? It's saying all it cares about is whether RA and RB can execute in parallel or not. It says sure, you can do it. So scheduler will look like this. Is it clear to everyone what is the rule of a scheduler? Right? Whenever I compile a rule, I get some guards coming out of it, which tells me whether the rule is ready or not. I feed all those signals into the scheduler. And scheduler has already analyzed your program, and based on that analysis, it generates a scheduler. Right? It says, oh, if these things are true, then you can it's okay to execute the associated rules, and so on. The effect of RB would be achieved automatically by the circuit I've already shown you. Okay, so slightly more abstractly, scheduler has lots of green signals going in, rules ready, rules ready, rules ready, right? And on the right hand side, signals are coming out, which are saying, yes, this rule is enabled. Actually, you can go and execute it. Will fire signals, we refer to them. All right? And guards of many rules may be true simultaneously, and some of them may conflict. BSV compiler constructs a combination of scheduler circuits with the following property. This property is a little bit of a mouthful, but it's not a difficult property to read. So think of it like this. If Bluespec compiler says it's okay to execute rule Ri and Rj concurrently, what conditions must be true? If Bluespec compiler says it's okay to execute rule Ri and Rb together, it must be the case that guards of both these rules are true at that time. Because if guards are not true, you're not supposed to execute the rules. So that's the minimum condition, that if I say these two rules can go together, then their guards must be true. What is the second condition? Conflict matrix must say that these two rules do not conflict. Because if there is a conflict between Ri and Rj, they can never be true together. So this information is statically being derived. I'm looking at your program, I'm analyzing your program, I being the compiler in this case, and I said, oh, in this case you can do this. And this property, using that, you synthesize a scheduler which every cycle decides, right, which rules can go, which part of the circuit will be active at any given time. Okay, so what I have shown you today is that you can have many rules active at the same time. Actually, my examples were rather simple. Maximum 3 rules could be active at the same time, right? But believe me, by the time you do big designs, by the time you do your design project, many rules will be concurrently active. And compiler will come to your rescue and say, oh, I can do the following rules together. And there are all kinds of annotations you can put in, which will, so that the output will tell you what is the guard of a rule and guard of a method, and which rules can be executed concurrently or not. You just have to type that when you invoke the BSV compiler. So the main takeaway is the semantics of Bluespec is derived from the fact that under all circumstances we believe as if one rule at a time was executed. Concurrent execution is never allowed to introduce new behaviors in this. This is a huge gain, because I can discuss extremely complex systems, and after thinking about it for a while, I said, just think of this rule firing, this rule firing, this rule firing, this rule firing, one by one. The fact that they all fired simultaneously, or some of them fired simultaneously, doesn't change the argument, right? Because you're assuming compiler is correct. If it does it together, it's preserving those semantics, one rule at a time semantics. Efficient hardware for multi-rule systems require that many rules execute in parallel without violating the one rule at a time semantics. BSV compiler builds a scheduler circuit to execute as many rules as possible concurrently. And for high performance design, we have to worry about the CM characteristics of a module. So what I want to do is, in the last slide, I want to show you how serious this issue is. And what do I mean when I say we have to worry about not just writing the code, we have to see what is its CM. So you are quite familiar with interfaces by now, right? Type, interface, and that's how you implement it, you write something. But now I'm adding one more property to the interface, and that is conflict matrix, which is printed for you. You don't write it down. You can see what is the conflict matrix. And let's look at it. So I started with this example, okay? And we said at that time, yeah, these rules can execute together, provided FIFO has the right characteristics, provided FIFO that you have designed can do NQ and DQ together. If you go and examine the FIFO that we had built for one element FIFO, its conflict matrix looks like this. And what does that tell you? It says forget about conflicts. NQ and DQ are mutually exclusive. They can't even be enabled together at the same time. Oops, that's a very big problem. I wanted to build FIFOs to connect things together, right? And the FIFO we built, it's correct, but from performance point of view, it doesn't do NQ and DQ together. Not very useful for building a pipeline system, the FIFO I showed you, right? So if you use this FIFO, there'll be no pipelining in that system, or not any significant pipelining, because stage 1 and stage 3 can still go on in parallel, even with this FIFO. But not all three cannot go on at the same time. So what you would really like is a better FIFO, and by better FIFO I mean whose conflict matrix may look like this, which says, oh, NQ and DQ don't conflict, they're conflict free. Wouldn't that be fantastic if they were conflict free? Because then I could use such a FIFO to build my pipeline systems. So stay tuned, that's what we're going to do later on in the course, but there are many other things to learn before that, because we really now want to put your knowledge of assembly language programming. By now you're all champion RISC-V programmers. And now you have learned enough about logic design, it's time to build a real computer. So from next lecture onwards, you'll be building a RISC-V computer. And please try this problem at home. It will tell you whether you learned today's lecture properly or not. It gives you step by step what you should do to see if these two rules can execute concurrently or not. Very good. Thank you.